All right, happy Tuesday, my aficionados. So once again, got a couple quick hitter videos for you today. This is something I've actually known about for a while, and I'm just now getting around to doing a video about it. I'm sorry, wish I could sort of present on these things faster than I do, but sometimes you just get a little busy with other things. So I'm doing this at the end of the day right now. I want to talk to you about using drift corrected frame integration and why sometimes it doesn't work as well as you would like it to, okay? And if you run into that problem, what you can do about it, okay? So we're talking about this within the context of Velox, okay? So when you acquire a series, whether you're in TEM mode or STEM mode, and this is usually more of a problem in STEM mode. I've rarely seen this be a problem in TEM mode because the acquisition times per frame in TEM mode are they're so short that you can collect, right, 10, 20 frames in a series in like 1 to 2 seconds. So this really isn't an issue so much with a TEM series, but this can be an issue with STEM because it's a serial process and it can take a significant amount of time per frame to record each frame, okay? So that's why this tends to be more of a problem with STEM and specifically with atomic resolution STEM with, a periodic structure, okay? So this is a series that I acquired from good old strontium titanate along the 001 zone axis or any permutation thereof you would like, okay? And so this is a 1K by 1K resolution, and this is 2 microsecond dwell time per frame, okay? So that's going to translate to approximately 2 seconds per frame, okay? So what's happening now, unfortunately, and this was taken on the Talos, so this is not taken with a CS corrected instrument, okay? So when the system does, or when Velox does frame integration, it is looking for detail in the picture in order to add the frames together. So right off the bat, if you don't have the advantage of CS correction, you're not going to have as much detail, and that immediately is going to put you in a hole, okay? I have noticed that this is usually not a problem ever with the Themis because we have the advantage of the CS correction, but I see this problem very frequently with the Talos, which does not have the CS correction and does not have the level of detail that we can obtain, okay? The STEM resolution at best is 1.6 angstroms at 200 kilovolts with the Talos. So, and if you look right here, this is the FFT, okay? You can see here that, and of course, we're not seeing a lot of detail owing to the fact that the signal to noise is poor in a single frame, but you can see very clearly that we're not seeing a lot of detail beyond 2 angstroms here, at least in the FFT of a single frame, okay? But anyways, let's go ahead, and you can see I've got 20 frames here. Now watch what happens as I cycle through the frames, okay? You can see very clearly, excuse me, that my image is moving, okay? My sample is moving, and it's actually moving in a quasi-chaotic manner, meaning it's not moving in a nice steady drift, okay? So that's another problem that I've noticed is that when the drift is not predictable or constant or stable, this also tends to have issues, okay? And unfortunately in the Talos, we're in the room with the microscope, and that's probably the biggest reason why we see this kind of instability. Even though I think the room, met all the specs when the microscope was installed. So anyways, but you can see very clearly as I'm cycling through this, right, the shifting between frames, it's not constant, okay? We're not getting like a constant drift in one direction here, okay? But anyways, let's go ahead and let's do the DCFI. Okay, so we'll go processing, DCFI. Obviously, we want to optimize for periodic images because that's exactly what we have here. If we just do regular DCFI, I mean, this won't work at all, right? Just to prove it, let me show you, okay? All right, so you can see very clearly, right? This didn't work at all, okay? So you've got to use the periodic option here with something like this, okay? So let me go ahead and get rid of this, and we'll go processing, DCFI, optimize for periodic images, okay? And let me switch to data bar. Now you can see there's parts of this that look pretty good, right? But if you look up here, let me expand this, you can see toward the top, this is looking not so hot, okay? It's looking not so hot. It's looking kind of smeared, like a little blurry, okay? And if we actually cycle through, let me start it at frame 1 here, okay? And watch what happens as, if you use the arrows just right, you can see, okay? You can see what's happening here, okay? Okay, so it's adding together better in some parts than other parts of the picture, okay? And clearly it looks better down here than it does up here. I hope you can see that, okay? So it's not doing the frame integration perfectly, okay? And the reason for that is, right, if you have distortion between the images that's not uniform, it's going to be hard to add the frames together, right? You're going to get distortion in your STEM images whenever there's drift, okay? So in other words, right, your square lattice is not going to be a perfect square if there's some movement, okay? But if it's worse frame to frame, then you can imagine, right, then if you try to add those two frames together, well, it's going to not add together properly, and you're going to have maybe part of your image that looks kind of blurry. And that's exactly what we have here, okay? This is actually a more mild example of this. I'm going to show you a more severe example of this in the next image. Let me save this, okay? So this is also same resolution, same dwell time per frame, and take a look at this, okay? And that's even worse, right? You can see up here how much smearing we're getting, okay? And it doesn't really look terribly good down here either, okay? And again, if we look at what's happening at the individual frame level here, you can see that's very chaotic movement going on, right? From frame to frame, okay? And so that's going to make it hard for the summation to be accurate when it's drifting in a manner like that, in a manner that's chaotic, in a manner that's not constant, okay? You know, doing the overlay or the addition of each frame subsequently is not going to be accurate, okay? And we can see that here very clearly, right? One frame looks fine, right? Because it's just one frame. And so 2 frames, so 3, now it's 4, it's starting to look a little iffy. Yeah, by 6, you can see clearly it's not working very well, okay? And so not good, right? So now the question then is, well, what do we do about this, okay? So if we have to be in the room with the microscope, well, that's not an option, right? We have to be in the room with a microscope. But what you can do, okay, the quicker you can make the time per frame, the less of an issue the instability becomes, okay? So how do you do that? Well, if you drop the pixel resolution down to 512 by 512, keep the dwell time the same, okay? Your time per frame is 1/4 of what it was before. And then it becomes, in this case, 1/2 of a second approximately per frame. Okay, so, and I actually have that right here. So this is now 512 by 512, 2 microseconds a frame. We're not really losing any detail in the picture. Okay, you can see in the FFT, right, my Nyquist limit isn't as big as it was, but based on the magnification, right, and the size of the pixels, I'm not really losing any detail in the picture, okay? And now if I cycle through this, you can see, because my time per frame is much smaller, the shift per frame is a lot less, okay? It's much, much less now than it was before, okay? So now, let's do the frame integration. And look at that, okay? this looks much better than what we were getting at 1K by 1K. Okay, looks much better. If you look at the FFT, I'm actually seeing better detail in the FFT here than I was at 1K by 1K, right? And if we actually cycle through each of the frames here, you can see those are adding together really, really well. Okay, again, this is non-corrected, right? So, it's not going to look as good as what we get in a corrected tool, but you can see how well this works, okay, or that this can be effective. So that's what I can recommend if you're having problems with the frame integration working properly, is drop the pixel resolution down to the next size, okay? You can keep the dwell time the same. You could also try dropping the dwell time the same, but keeping the pixel resolution the same. That could also be effective. I find that reducing the pixel size to the next level tends to be a bit more effective than simply dropping the dwell time, okay? Because your signal per pixel is not going to suffer as a result of that, right? Because you're still getting 2 microseconds per pixel, okay? So that is the video I wanted to do about what happens when DCFI, doesn't quite live up to the hype, and what you can do to work around that, okay? So hope you found the video useful, and I'm going to do another one here in a second talking about filtering we can do to the images. So take care, everyone, and stick around soon here.